Hi, welcome back to Engineering 255. This is the second video of the chapter 9, and we're going to focus on 9.2, which is the composite bodies. In this video, we're going to look at if you have a shape, and this shape is arbitrary, but it can be decomposed into some simple shape. Then we can use a way to calculate the center of the mass. So let's look at how we do that. So we are going to focus on 3 points. The first is how do we find the location of the center of the gravity, and which is going to be the center of the mass because the gravitational field is going to be very similar. And we also going to look at the location of the centroid using the method of the composite body. At the bottom, you can see two shapes, which are like an example, things like this one here, that you see it on the road. Then the center of the gravity is right at here. So how do we actually determine the center of the gravity? Right at here, right? Vertically, you probably know it's symmetric, but how far from the base or how far from the top is going to be the key point. There are a lot of application about this. In the next chapter, we are going to talk about another idea called the moment of the inertia. This idea is important because the material has a different strengths in different orientation. And you know that when you look around those structure, we don't normally use a solid beam. We usually use this so-called structure beam. I-beam and T-beam are very common. The reason that we use that is because a certain orientation, the strengths of these beams are strong. Instead of using a solid material, which will waste a lot of cost, and this actually would do similar functions and is with a less of the mass that you need. So if you use these kind of things, then how do we determine the center of the mass to put the consideration of the weight of these kind of a material? And the most important is when you go to the next chapter that we have to use this idea to determine the moment of the inertia. Same thing, if you have very complicated layout for different machinery in a structure, how do you analyze the force? It will depend on the location of the object, the shape of the object. So to determine the location of the center of the gravity, it's going to be a key thing for the analysis. So the theory or the equation to find that is very simple. We start by looking at the resultant weight, which is the total force. If you have a couple different objects, let's say this 3 different objects that you see in the picture, it could be like a 3 different machine on the floor, right? It could be like a compressor, and then you have a boiler, and you have another probably a generator. They all on the same floor, maybe on a different floor, right? It's a different height, maybe on the different floor and a different location on the floor. And how do you find out the total center of the mass? The total weight is very simple. You just sum the weight of individual one. That will be the WR, which represent the resultant weight. And if you want to sum the moment, and then you have to look at which axis that you are trying to sum them. So in this example here, that we are summing the moments about the y-axis, right? Y-axis. So if you look at the y-axis, which is this one here, and let's say we try to find the location of the x, which is the g here, is the center of the gravity or the center of the mass in this case. and we want to find x bar. And this is the location that with respect to the y-axis. And then you find the moment for each one of the small component, and then you make it equal to the total component at the center of the gravity multiplied with the center of the mass location. That's what we talked about in the previous video, actually. So then you can find out the center of the mass or center of the gravity location, which is equal to the total mass at the bottom. And on the top, you just simply find out each one of the individual mass multiplied with the location of the object at the x direction. For y, you multiply with y. For z, you multiply with z. And that's very, very simple equation. So the top one represents the moment, the bottom one just represents the total mass or total weight. So practically, how do we use those ideas? How do we do the calculation? I want to start from the right-hand side first. This is the picture that you saw before. So those roadblock, if you have a roadblock like this one, and you see is a symmetry to the y-axis, but in x-axis, yeah, it's symmetry to the y-axis, and in the x-axis, it gives you the dimension, and you see there's a point that we refer to the corner point of the shape. Then how do we find out the center of the mass for this one here, which is going to be in the y-axis? How do I find out the height of that and the y-axis to be the center of the mass? Because we know the center of the mass is going to be just right in the middle in the x-axis. But what about the y-axis? And if you think back to the equation that we talked about before, and the y bar you want to find out is equal to the total weight of this one here is the y times dw, right? Which is the individual weight. Okay, now in terms of this, what does that mean? Now you can think about the shape of this one to be some simple shape. This will be one of the shape. And here you have, let's just make the one of the single shape as this one. This is the one of the single shape, right? Rectangular one. And I have another one which will be a triangle one. And there's another triangle one. And then I have a rectangular one on the left. I have a rectangular on the right. So now I can make this dw as a 5 component, and that's A, B, C, D, E. I have 5 different components. And the total weight of these is the summation W at here. I can find out the weight for each one of this component because I have the dimension of that. Now we know the weight of these things is proportional to the area by assuming this thing just extended to the same depths, right? So if it extended to the same depths, this dw is simply just equal to the area times whatever the depth is times the density, and they all have the same density by assuming this is homogeneous, and they all have the same depths. So when you put the depths at here, density at here, depths at here, density at here, they all cancel out. So we can simply just simplify this one to be like a dA over the summation area. Then this problem will be very simple to solve. Similar to this one here, now this one is different from the right-hand side. The right-hand side, we kind of decompose into 5 different shapes with something together. Now, on the left-hand side, you have a hole in here. So instead of adding all together, when you have a hole, we make a subtraction. So you can say the total area of this one is going to be A, which is the semicircle here, plus B, rectangular, plus C, triangle, and minus a hole at here. And that is the simple idea that will help you to solve the problem by the idea of the composite body. So the step to analyze these kind of things is that you're going to divide the total body into smaller pieces, and the smaller pieces will be the shape that is easy to calculate its area or its volume. The whole is going to be something negative that you're going to take it out, so you're going to do a subtraction. If they are not a whole or some kind of cut out parts, and you're going to add them together. It doesn't have to be a whole, okay? It does, well, I should say it doesn't have to be like a circular. It could be a rectangular. It could be a triangle as well. But you just kind of a negative by doing the subtraction. Then you make a table. I think the table is actually the best way to do this calculation. And we will show you a table after this. Then, and you have to find out the distance. Remember, if you have, let's say, this is the coordinate that you have, and if you choose the coordinate like this, because you have to find out the location, you certainly have to have a reference point. This is the X, this is the Y, and then you have a shape, let's say an arbitrary shape like this one here. I make this one simple. You have two shapes, one rectangular and the other one is triangle. You make a coordinate axis by selecting this one as the origin. Then this shape is going to be away from this point, from the center point about this much. And the second one is the triangle, right? And the triangle has a center of the mass, which is 1/3 to the base. So the second one also have x-axis like this. So this is what we mean that you fix the coordinate axis and you're going to determine the center of the gravity, the center of each one of the shape. Each one of the shape. Rectangular just right at the middle of the shape. Triangle is going to be 1/3 from each one of the base. So this is one of the base, this is another one of the base. So it's going to be 1/3 from here, 1/3 from here. Then you can find the location of each one of the centroid of the shape. And then you just use this equation to find the solution. So for the x, you put x multiplied with that. This one simply represent these location that we just talked about. Okay, let's look at an example that you will see how easy that is. Okay, so the first example you see here that we have a three-dimensional shape, right? And you can obviously see that this three-dimensional shape can be separated into three simple shapes. The A is a triangle and B is just rectangular. C is another triangle. They orient at different location, different orientation, right? So we can like dissect this one into like three different pieces. And then we just make a table to do the calculation. So again, let me just draw the shape again. So this is the shape it looks like. You have a rectangular one here, and it's just like this. And triangle over here. And another triangle here. Okay. All right. So A and B and C. So for the A, you find the volume because there is a depth, and the triangle, you just find this triangle area, you multiply with the depth, then you got the volume. So you got the volume is equal to this. And you have B, which will get the volume. This thing three should be very simple. Now over here, this one is the X tilt, like the centroid of each one of the piece, and you look at each one of the orientation. So for the A here, I didn't include the dimension here, but for this one here, I guess the X is in this axis, this will be the Y, this will be the Z, and you have triangle. So this one had to be careful because it actually starting from here is not from the origin. So you might need to add this amount and you look at what this shape is and find the 1/3 from the base, and that 1/3 from the base plus this distance is going to be your X bar. That's your centroid of that piece. Same thing for the Y, so the Y is going to be 1/3. No, for the Y here, this is the Y direction, right? The Y is going to be just right in the middle of this here. So I guess this one is 0.5 meter, so your centroid is going to be 0.25 meter. For the Z is going to be, again, is going to be 1/3 from the bottom here. So you look at this one is 0.6. So if that's 0.6, I'm guessing the height of this one is going to be 1.8. It's going to be 3 times 0.6. So I think that is correct, because if you look at the shape of B, the Z centroid is going to be rectangular, is going to be half of the height. So 1.8 is the height of this one. So centroid of the B component at the middle is going to be 0.9 at here, just right at the middle. I'm guessing the width of this one is 2.5. So in the middle of this one is 1.25. And for the x-axis, it depends on the thickness of this one here. So the thickness is 0.5. So it will be half of that is 0.25. So same thing for the C. You just have to be careful of the orientation. The C is different from the orientation of A, but the idea is the same. And then what do? Then the next step is that you multiply this one with this one, and you put a value at here. And that's what you have. This should be X tail times the V. This will be the Y tail times V. This will be the Z tail times V. You calculate each one of this value, and then you do a summation. So this summation is actually, when you do X bar, is going to be the summation of the volume. And here, this will be summation of X tail V, and that is this one here. And this one is going to be this value. So if you want to find the centroid of the X location, it's going to be 1.406 divided by 3.6. This is a meter force. This is a meter cube, and you're going to find the meter, which is the centroid location of the X. And same thing for the Y, and same thing for the Z. And that's how easy that you can do. If you have a composite body, you just make a table, follow the same instruction. Just make sure, like, the tricky point for this question is that this triangle does not start from the origin. It actually has an offset right here. You have to add the width of that. So here is the result, and that is